Just look at this. It's incredible, right? It's like a microscopic ballet, a whole digital universe where we can watch the fundamental dance of life playing out. We can simulate pretty much anything: how a drug latches onto a protein, how a cell membrane actually holds itself together, all of it at the atomic level. It is unbelievably powerful.
But, that raises a huge question. A computer, it's just a machine, right? It's running on ones and zeros. So how on earth does it know how two atoms are supposed to push or pull on each other? How does it know the fundamental rules of chemistry and physics? Well, let's get into it.
The secret sauce. The answer to that question is something called a force field. Now, it's not some shimmering sci-fi shield from a movie, but honestly, it's just as important. A force field is the engine, it's the rule book that governs every single interaction in these tiny simulated worlds. And that's exactly what we're going to break down today.
So here's the game plan. We'll start with what these simulations actually are. Then, we'll dive into the force field engine itself. We're going to dissect its parts, see how it's tuned to match the real world, talk about what happens when models go wrong, and finally, we'll tackle one of the biggest computational hurdles: long-range forces.
All right, Section 1, the digital molecular world. So what are we really talking about when we say we simulate molecules?
The technique is called molecular dynamics, or you'll just hear people call it MD. And at its heart, it's actually about applying a really simple law of physics over and over and over again. For every single atom, the computer calculates the total force that's pushing and pulling on it from every other atom. Then, using Newton's classic equation, the one F equals ma, it predicts how that atom is going to move over an infinitesimally small step in time. The real magic and the whole challenge is figuring out that F, the force. And that is where force fields come in. You just repeat this process millions of times, and boom, you get a movie of a molecule in action.
Okay, Section 2, the force field engine. Because as I said, calculating those forces is the key to this whole thing, and for that, we need the rulebook.
A force field is, at its core, a big, complex mathematical equation. And what it does is approximate the potential energy of the entire system. Think of it like this: the force field describes an energy landscape, kind of like a terrain map with hills and valleys. And you might remember from physics class that things always want to roll downhill to a lower energy state. Well, the force is just the direction and the steepness of that hill right where the atom is sitting. So if you have the energy map, you can figure out all the forces. The force field is really the core assumption that underpins every single one of these simulations.
All right, Section 3, anatomy of a force. So what's actually in this master equation? Let's pop the hood and break it down. You can think of it like a molecular instruction set.
It's really split into two big categories. First up, you have the bonded terms. These define the molecule's own structure. The chemical bonds holding it together, the angles between those bonds, and the way the bonds can twist around. They're like the molecule's skeleton. Then, second, you have the non-bonded terms. These describe how atoms that aren't directly connected interact with each other, both within the same molecule and with all of its neighbors. This is where those classic forces you've heard of, like van der Waals and electrostatics, come into play.
And this is how it all fits together. The total potential energy of the system, which we call V here, is just the sum of all of these individual pieces. You calculate an energy term for every single bond, every angle, every twist, and every pair of non-bonded atoms, and you just add them all up. This is the typical structure for what we call a Class 1 force field, which includes some of the most famous ones out there, like amber, charm, and OPLs.
Okay, Section 4, tuning for reality. So we've got the form of the equation, but where do all the numbers come from? How do we know what the ideal length for a carbon-carbon bond is, or how strong an electrostatic pull should be? That's where a process called parameterization comes in. These parameters are definitely not just pulled out of thin air. They are meticulously, painstakingly tuned to reproduce reality. Scientists use super high-accuracy quantum mechanical calculations on small, simple molecules to get a baseline. They look at real-world experimental data from things like spectroscopy, and this is a big one. They run simulations of simple liquids, like a box of water, and they tweak the parameters over and over until the simulation's properties, like its density or boiling point, match what we see in the lab. The dream, the ultimate goal, is to create a set of transferable parameters that works accurately for a huge range of different molecules.
And this brings us to a really fundamental trade-off in molecular simulation. On one hand, you have all-atom force fields. The name says it all. They model every single atom. This gives you amazing detail and high accuracy, but man, it is computationally expensive. On the other hand, you have coarse-grained models. These group several atoms together into a single bead. Now you lose some of the fine detail, but it is way, way faster. That lets us simulate much bigger systems for much longer periods of time. It's always a balancing act between accuracy and speed.
So, Section 5, when models go wrong. And this is something you absolutely have to remember. Force fields are incredibly powerful, but they are still approximations of reality. They are models, and like any model, they have their limits and potential sources of error.
This quote from a landmark 2003 review by Ponder and Case just says it all. They took a small peptide and simulated it with 3 of the most popular force fields out there. And the results? They were all different from each other, and all of them were different from the more accurate quantum mechanics calculation. Now, this doesn't mean the force fields are bad. It just shows they're different models, each one optimized with different data and different philosophies.
And that leads us to the single most important rule if you ever do this kind of work. A force field is a self-contained holistic package. All the parameters, the bond lengths, the charges, the van der Waals terms, they were all optimized together to work as a team. You absolutely cannot take the bond parameters from, say, Charm and the charge parameters from Amber, stick them together and expect to get a meaningful result. It is the #1 rule of MD. Never, ever mix and match.
So when things do go wrong, the errors usually fall into one of 2 buckets. First, you have systematic errors. These are baked right into your setup. They come from the tiny inaccuracies in the force field itself, or choices you made, like how you handle those long-range forces. Running your simulation for longer isn't going to fix these. Then you have finite sampling errors. This basically means your simulation just wasn't long enough to see all the important shapes and movements the molecule can make, so your results are incomplete or biased.
All right, that brings us to our final section. And honestly, it's one of the biggest headaches in the whole field and a huge source of potential systematic error. How do we deal with long-range forces?
See, calculating the interaction between every single pair of atoms is the most time-consuming part of any simulation. Now, for the van der Waals forces, those fleeting attractions and repulsions, they drop off really, really fast. So we can safely just ignore interactions between atoms that are far apart by using something called a cutoff. This saves a massive amount of computer time. But electrostatic forces, the ones from positive and negative charges, they decay very, very slowly. If you use a simple cutoff for these, you can introduce huge, totally unphysical errors into your simulation. And this graph shows the problem perfectly. That solid green line, that represents the true potential energy between 2 particles. The other dashed lines show what happens when you just chop off the interaction at a certain distance. You can see they're way off from the real value. They completely distort the energy, and as a result, the forces. For electrostatics, doing this is an absolute recipe for disaster.
So how do we get around this? Well, the standard solution is a family of really clever methods based on something called Ewald summation. The most popular one is particle mesh Ewald, or PME. The math gets pretty hairy, but the core idea is genius. It splits the calculation into 2 parts, a short-range part that's calculated directly, and a long-range part. And for that long-range part, it uses a mathematical trick called a Fourier transform. It's kind of like describing a complex musical chord not by where each string is, but by the combined frequencies that make up the sound. It's a much more efficient way to capture the overall pattern, and it lets us accurately account for every single electrostatic interaction in the box without those dangerous cutoff errors.
And that leaves us with this final, fascinating question. Force fields are, at the end of the day, a clever and computationally efficient approximation of the quantum mechanical world. They're the engine that has powered molecular simulation for decades. But as our computers get exponentially faster, will we one day be able to just ditch the approximations altogether and simulate everything from pure first principles quantum mechanics? Or will the sheer scale of biology mean that we will always need these clever, elegant, and powerful engines to get the job done?